This is day 1 of section 2.3, and in section 2.3 we talk about the concept continuity. So if we think about continuity, we're going to ask ourselves, how can continuity of a function be determined, and what does it mean for intermediate values within the domain? And we'll get to that part of the question on day 2. So to start thinking about what continuity means, just kind of think about how many numbers are there between 1 and 7 inclusive. So if you count from 1, starting at 1 up to 7, how many numbers do you count? And some might tend to think that it's just 1, 2, 3, 4, 5, 6, and 7. But really, there are numbers between 1 and 2 and 3, and 3 and 4, and so on. So every time we look at a number line, we can always subdivide it and find something in between the two numbers we just mentioned. Between 1 and 2, there's 1 1/2. Between 1 and 1 1/2, there's 1 1/4, and so on. So there are really infinitely many numbers between 1 and 7. Likewise, if we look at the visible spectrum, some people might think there are only 1, 2, 3, 4, 5, 6, 7 colors in the visible spectrum, when in reality, there is a continuum between red to orange to yellow to green and so on. So there are infinitely many colors in the visible spectrum. So when we talk about a continuous function, then, we talk about something that has infinitely many values that is never interrupted. So I pose this visual question then, or this visual concept as kind of a working definition of continuous. If you can draw a function without lifting your pencil, then you've just drawn a continuous function. So in other words, we've already talked about, in section 1 and 2, we've already talked about functions that have holes in them and functions that have asymptotes in them. Those are locations where you'd have to lift your pencil. So those are points of discontinuity. In other words, points where the function fails to be continuous. So that's kind of a working definition, and we'll rely on that pretty heavily. But here's the mathy definition. In other words, if we can't have any holes, like for instance, take point C here, and C is in the interior, so we're looking at this part of the definition here. If this is an open hole, then as I draw this, I would have to stop here, jump over, and continue drawing. So as I approach a value, this better not be an open hole. It better be filled in so that I can continue my pencil straight through. So if we look at point C then, what we see is that the left limit and the right limit have to go to the same value, and the hole needs to be filled in, which means the function has to have that same y value. So the math definition of a continuous function in the interior is that the left limit is equal to the right limit, and that's equal to the function value. So that is our mathematical definition of continuity. Now, the definition of continuity at an endpoint gets slightly modified, because we're going to talk about functions over a finite domain. In other words, we're going to talk a lot about functions that start at one point and end at another point, and what happens outside that domain we don't care about. So if we're looking at an endpoint, we can say that a function is continuous at an endpoint as long as that endpoint is filled in, as long as it's not an open dot. So in other words, as long as this limit matches the function value. So the limit, and of course this limit's approaching from larger values of a. So this would be the right limit as we approach a equals the function value at a. Or for the other side, it would be the left limit as we approach b equals the function value at b. So no open dots is what we're really kind of, if we want a working definition for continuity, no open dots. So those dots definitely have to be filled at the end in order for us to say that the function is continuous at the endpoints. So most of the techniques in calculus require us to have a continuous function. So that's pretty important. And like I said, the working definition here is a continuous function if you can draw it in one motion without picking up your pencil. So let's take a look at this piecewise function below. It's a piecewise function. It has a finite domain. Finite meaning that the domain begins and ends at values. So it begins at x equals 0, ends at x equals 4. So is there anything about this piecewise function any point at which you have to pick up your pencil? So if I start drawing here with my pencil, I start at x equals 0, I fill in this dot, I come down here, I come to an open dot, and then I've got to jump up here, and I've got to fill in this dot. So I just had to jump. So I had to lift my pencil in order to do that. So there's one point of discontinuity. And then as I continue to draw, fill in this dot, come across here, here's an open dot, causing me to jump up to here to draw on a function value, and then jump back down to here to continue drawing up here. So there's another point where I had to lift my pencil. So that's another point of discontinuity. And then I can keep drawing, fill in this dot, keep drawing, fill in this dot. So I'm continuous all the way till the end. So I have 2 points of discontinuity here. And so I have a point of discontinuity at x equals 1 and a point of discontinuity at x equals 2. So that's kind of a visual representation. Now we'll talk about what to name these discontinuities in just a second. So if it's removable, that means we have a hole. And we can always fill in a hole. You can always define a function at a point and fill in that hole. So we call those removable discontinuities. And then the other ones, I'm not quite sure why. I would just call them not removable, but the book terms them essential discontinuities. In other words, they have to be there. They're part of the characteristics of the function, and they can't be removed. So one is a jump. Anytime you see a jump, you can't remove that. You can't take it out. Another one is an asymptote. Anytime we come up with an asymptote, we can't remove that. That's part of the characteristic of the function. Another word for an asymptote discontinuity is an infinite discontinuity. And then the last one's an oscillating one. So as this one oscillates, it comes in and all of a sudden it has a gap here where it's not defined. If you can see the function here. If we put in 0 here, it's not defined. So we have this point of this function that's not defined, and so that gives us a discontinuity as well. Almost like a sideways jump. So let's talk about removing a discontinuity. The only type of discontinuity you can remove is a hole. And so the first thing we have to do is see if we can find a simplified expression for this function to see if we have any holes in the function. So we're going to write that extended function. So we're going to factor the top and factor the bottom. And factoring a cubic, I don't have you do too often. So don't stress too much about having to do that. So let's take a look at this. So we're saying that this function, this rational expression, has a discontinuity at x equals 1. So let's see what's happening at x equals 1. Let's take a limit as we approach 1 and see what happens to this value. So I'm going to go ahead and factor the top and bottom and look at my factors, and I see a duplicate, so those cross out. So we know when factors cross out, we have a hole. So in this case, if I put and I'm looking here at this approach to value, if I put 1 in for here, I get 0, and I get 0 here. So at x equals 1, we have a hole. And we can remove a discontinuity that is a hole. But we also have a different discontinuity, that this factor that doesn't cancel gives us an asymptote, and that's not removable. So let's take a look at how to remove this hole, kind of plug it, so to speak. So if we cancel factors, we have a discontinuity that can be removed. So what we do then is, here's what we're left with after we cancel the factors. And we're going to evaluate that at 1. And we can see then that we have to draw a hole. If we plug in 1 for x's here, we have to draw a hole at a y value of 3/2. So what we can do then, if we need to plug this y value so that we can remove the discontinuity, then we need to write a piecewise function. So the piecewise function kind of looks like this. We define the function for all values except for where the hole is. And then at the hole, we define a single y value of 3/2. So that's literally an x coordinate of 1 and a y coordinate of 3/2. And so, and then we'll talk about this other discontinuity at -1 here, this asymptote. So let's take a look at what this looks like. Here's the function. Okay, here's our math that we did on the previous screen with our canceling factors. And so that means that we have a hole at x equals 1, because we took a limit as x approaches 1. We found some canceling factors. So that's where our hole is. So in order to plug that hole, we define a single value 3/2, and we can fill that hole in. And so that's how we make a discontinuity. That's how we remove a discontinuity. Okay, the other factor that does not cancel is an asymptote, and that can't be removed. So here's the asymptote at -1. So we have one removable discontinuity, and we have one essential discontinuity for this rational expression. So nope, that asymptote is not removable. So the summary, I think we're actually going to save until the end of section 2-3. I don't think you have a summary box at the bottom of your that page anyway in your notes. So we'll leave that until the end of section 2-3. And at this point, you can do the homework. It's section 2-3, just the day one. It's going to be a 2-day section, so we're going to have 2 homework assignments. So just that first homework assignment for tonight.